Dear all, Jona and I, working at the KU Leuven in our research group DRAMCO, have contributed to the Interreg NOMADe project. We made battery-powered motion sensors which could be placed on patients with a capturing platform and a connection to the cloud. The heart of these systems is the sensor itself, who is able to detect motions. In this presentation, we are giving a short introduction and discuss the basics about internal measurement units. Here you can see our NOMADe motion sensor platform, where each motion sensor contains an inertial measurement unit. The data capturing unit captures the motions information from all connected sensors at the same time. In this presentation, we will focus on one component from the motion sensor PCB called the inertial measurement unit. We start with an introduction and go further on the technologies used to capture the motion. Jona will speak more in depth about the sensors actually work and on the basis of an example of an existing internal measurement unit IC. We then lastly speak about how to use the process the data. Let's start with the purpose of an IMU. The three parameters that you can measure are the angular velocity, acceleration, and magnetic field. A gyroscope measures the angular velocity, an accelerometer measures the acceleration, and a magnetometer measures the magnetic field. Furthermore, an IMU can be used to calculate an orientation. Therefore, it should combine these sensors. Also, position estimation, assisted GPS, for example, is one of the possible applications. To give an idea about the importance of these systems, we give here some use cases. When measuring orientation, for example, they can be very useful in stabilizing a drone. Gyroscopes and accelerometers get used all the time in airplanes to measure angular rate and accelerations. All existing smartphones contain an IMU to, for example, detect when your phone is in portrait or in landscape mode. Finally, in cars, in navigation purposes, the IMU detects the current vehicle orientation. How is an IMU actually made? The first IMU dated from the early 19th century. As you can see on the picture, they were at that moment very big, bulky, and not that accessible. The rise of micro-electromechanical systems has been a huge step forward in electronic miniaturization. The first MEMS were commercialized in the 80s and now used in many applications. MEMS devices can be subdivided into four categories. The sensors used in IMUs consist of transducers converting energy from one form to another, also called sensors and actuators. For example, converting acceleration into an electric voltage. Further, the MEMS microstructures are, for instance, cantilevers, diaphragms, springs, spirals, etc. And lastly, the microelectronics is the integration of electronic components and MEMS devices. Let's take a look to an example of a microsensor. A typical MEMS accelerometer is presented here. It consists of an integrated circuit, which comes from a wafer. A wafer is a round piece of silicon in which electronic circuits are manufactured in batch. This wafer is sliced into single chips, which are called dies. These dies are further encased to be able to solder them on a printed circuit board. Here you see another example of a full MEMS IMU. Later in this presentation, we will go into more detail about how each type of sensor works. Other examples of MEMS sensors are temperature or pressure sensors. This MEMS technology has a lot of advantages in comparison to the macro-scale counterparts. To start with the performance and accuracy, which are typically higher on MEMS devices, MEMS sensors result sometimes in lower cost per device. Also, the smaller form factor is, of course, very appealing. Even sensors and actuators can be integrated together with small electronic circuits on the same silicon, which has opened a world of possibilities. A further detailed discussion of the operation will be covered by Jona in the upcoming slides.
The accelerometers in typical IMU use the principle of capacitive sensing to convert accelerations into capacity differences. A stationary plate, here denoted as the fixed electrode, is used in combination with a moving plate indicated as the seismic mass. The space between the two plates forms a small capacitor. Changes in acceleration cause a variation in the distance between the two plates, which in this case also creates a varying capacitance. This capacitance can be converted into an electrical voltage and sampled by an ADC to be converted into a digital signal. A typical MEMS gyroscope measures angular rotation in the same way as the previously mentioned accelerometer. The angular rotation is measured by means of Coriolis acceleration. A frame which can move, containing a resonating mass, is attached with springs to a fixed frame. The green arrows indicate the force applied to the structure based on the status of the resonating mass. The displacement of the central mass changes with changing angular velocity. Therefore, the distance from the moving mass to the fixed plate changes. These changes are capacitively measured by using sense fingers, following the same principle as previously discussed. Magnetic fields typically get measured by means of the Hall effect. The Hall effect is a production of a voltage difference across an electrical conductor that is transverse to electrical current in the conductor and to an applied magnetic field perpendicular to the current. This voltage difference is a means for the magnetic field, and therefore with the help of an ADC can be converted into a digital signal. In what follows, we're going to discuss in more detail the IMU structure, looking at common types, datasheets, typical settings, and finally the calibration. Generally, two main types of IMUs are available. We have the 6 degrees of freedom IMUs, which include a gyroscope and an accelerometer. And then we also have the 9 degrees of freedom IMUs, which next to the gyroscope and accelerometer also include a magnetometer. Taking a look at the datasheet of the NOMADE IMUs, since this is an example of a digital sensor, the analog sensor values need to be converted to digital values by means of an ADC or an analog to digital converter. We also want to measure angular rotation, acceleration, and magnetic fields in 3 directions, the X, Y, and Z direction. Therefore, an IMU includes 3 gyroscopes, 3 accelerometers, and 3 magnetometers, with each dedicated ADCs. A temperature sensor for temperature compensation is also included. A special feature of this IMU is the included digital motion processor, denoted as DMP. This is a dedicated processor which can process the raw data, meaning the gyroscope, accelerometer, and magnetometer data, into, for example, a rotation or an orientation by means of sensor fusion. We will shortly go into more detail about the sensor fusion. Several configuration registers are also available to, for example, set the full-scale range, which is related to the sensitivity of the sensors, to set the desired output frequency, or to store the calibration offset values. Here we can see some typical settings. For example, the full-scale range of the gyroscope can vary from plus minus 250 degrees per second to plus minus 2000 degrees per second. Looking at the output data rate for the gyroscope, which can vary from plus minus 4 Hz to half a kilohertz. A very important topic regarding sensors is the use of calibration. We use calibration to ensure the sensor performs according to the specifications and to provide meaning to the electrical output. Several types of calibration errors can occur within the different types of sensors. The gyroscope and accelerometer typically suffer from offset and scale errors, while the magnetometer suffers from hard and soft iron distortions. Gyroscope offsets, for example, occurs when the gyroscope readings are not zero when no angular velocity is applied. The scale factor applies to the proportional change in gyroscope output values with regards to the input values. On the magnetometer, two similar types of calibration errors can occur, hard and soft iron distortions. When plotting the magnetic field in 3 axes, it should form a perfect sphere. Hard iron distortions create an offset in the sphere when, for example, a permanent magnet such as a speaker sits in a fixed place in the reference frame of the magnetometer. Soft iron distortions can be caused by magnetic objects which are not fixed to the reference frame of the IMU. They distort the sphere, turning it more into an ellipsoid. Some calibration values, such as the basic sensor offsets, can also be set in the user configuration registers of the IMU directly. The IMU will then automatically adjust for the configured offsets. Note that not all calibration errors can be set in configuration registers directly. As can be seen by the current consumption of this IMU, it doesn't use a lot of energy, which is ideal for embedded battery-powered devices. Here you can see an overview of the NOMADe sensors. The whole system is battery-powered. The different chips are powered by a stable 1.8 volts provided by the voltage converter. Bluetooth Low Energy connectivity for sending the IMU values wirelessly is included by the nRF52 chip. When the battery gets empty, the system can be wirelessly recharged via a Qi-compatible charger. In what follows next, we're going to take a look at the IMU processing, meaning how the raw data gets converted into an orientation, how these algorithms work, and which algorithms we can use to do it. The raw data gathered from an IMU may sometimes not be enough, depending on the application. When, for example, an accurate orientation is required, some sort of sensor fusion has to be applied on the raw data. Typically, a Kalman filter, a complementary filter, or a Medwick filter can be used. The result of the sensor fusion is an orientation or rotation info. Orientation or rotations can be represented several ways, by using quaternions, by using Euler angles, or by using tight Bryan angles. To quantify the difference between rotations and orientations, rotations concern relative values, in contradiction to an orientation, in which the rotations are referenced against a reference placement. Euler angles are the simplest way of representing orientations or rotations by a rotation around 3 angles: a yaw, pitch, and roll angle. Unfortunately, a problem can occur in a specific situation when 2 axes overlap each other. At this moment, a degree of freedom is lost, and the Euler angles are no longer effective. A better way of uniquely describing orientations or rotations are quaternions. This representation uses complex numbers, but is a lot harder to understand than Euler angles. The benefit here is they do not suffer from the problems that the Euler angles had. The simplest way of calculating a rotation is by integrating the gyroscope values. Unfortunately, when integrating over a longer period, the very small errors from the gyroscope can become fairly significant. The accelerometer and magnetometer are typically included to correct for these errors. Depending on the sensors included in the IMU, multiple corrections can be applied to increase the accuracy of the orientation. From the accelerometer data, when not in movement, an orientation can be calculated, which will be reliable for the roll and pitch axis. Since the Earth's magnetic field does not change, a magnetometer can be used to correct the errors in the yaw direction. Since a 6 degrees of freedom IMU does not include a magnetometer, there will always be a small drift in the yaw direction. Here you can see the different data output types supported by the NOMADe sensors. We have the quaternions 6 degrees of freedom, quaternions in a 9 degrees of freedom. Next to that you can request the raw data, which consists of the gyroscope data, accelerometer data, and magnetometer data. All sensor data are available at both 50 Hz as well as 100 Hz. Now that we have explained all of the IMU, what can we do in post-processing with the data? A couple of examples are given, such as a threshold detection algorithm, recognizing patterns with machine learning, and detecting entropy. The threshold detection algorithm can detect if a certain parameter or metric is above or below a set threshold value. For example, when stretching a body part, one can detect if this body part is sufficiently stretched or not. The next technique that can be used is machine learning. By mostly using neural networks, things such as activity classification can be done to detect if you're, for example, running, cycling, or walking. Most people are spending a considerable amount of hours at their desk each day. Lower back pains can be the result of this. By calculating the entropy of measurements during a whole day, a physiotherapist, for example, can get a picture of how much you're moving. The variance in movements is measured, and therefore it can also detect consistency of exercises. We hope this video has explained the IMU sufficiently, how it works, what can be measured with it, as well as some post-processing options.